Hello, everyone. Welcome to our live session for Wednesday, June 2nd. We are excited to have you here, and my name is Matthew. I am one of the instructors for the online classes that we teach. I also help out behind the scenes. We've got Victoria, who's on with us today, who's helping out behind the scenes. I'm going to hand this over to Professor Impey, who will welcome everyone, and then we will get started with your questions. Please post those in the Twitch chat, and we'll grab them from there.
Okay, welcome everyone. This week I'm in Aspen at the Center for Physics here, and will be for a few more weeks, so I guess we'll have another session from here too. Nice and cool, break from the Tucson heat. And for all the astronomy enthusiasts out there, this is another live session Q&A, and the floor is open for your questions.
Excellent. The first question is from Lorentz 4040. Would like to know, does the cosmological constant mean that the mass energy density of the universe is constant? And how does that relate to dark energy in an expanding universe?
The cosmological constant was a mathematical artifact. It was an integration constant in the equations of general relativity. Because when you solve those equations, it was actually first done correctly and properly by Friedman, rather than by Einstein himself, you have dynamic solutions. So you either have an expanding or contracting solution for the universe. Because Einstein had been told by the astronomers at the time, in the early 1920s, before Hubble discovered the redshift of galaxies, that the universe was static, he included that constant of integration to suppress what would be the natural expansion. And so it works in the opposite sense to gravity. And so it's a constant, it is indeed a constant energy density, and that's what the cosmological constant is. Now, that's not a physical theory for dark energy. We still don't have a physical theory for dark energy, but as far as we can measure its properties, it does seem to be constant over time. So as space expands, the amount of dark energy or repulsive force within that space increases, and that's why we have an accelerating expansion.
Excellent, thank you very much. Hamid Mazouji sent an email asking about Lagrange points. So there's some specifics here, but the first question is, can you just talk about what Lagrange points are and why they are important?
So these are mathematical solutions for gravity when you have three objects or more, actually, but the simplest solutions are for three objects. The reference and the person who came up with these ideas is referencing a French mathematician from the 18th century. And so in a situation like Earth, Sun, Moon, which is the classic situation, you can have balance points of gravity between the Earth-Moon system or on the far side or on either side. Two of the Lagrange points are stable, which means that an object placed there will be in a gravitational balance and won't move. And two of the Lagrange points are unstable, which means that equilibrium is unstable and any small perturbation will lead the object to move away. For satellites and space missions where you want some distance from the contaminating and noisy and polluted environment of the Earth, then the Lagrange point is favored. And so James Webb Space Telescope is at a Lagrange point, and a number of satellites have been at the L2 Lagrange point, and that's about 1 million kilometers from the Earth. So these are quite popular solutions for satellites when you want to be in a stable or quasi-stable orbital configuration, but removed from the Earth system for reasons of noise suppression and darkness and so on.
And so specifically, he would just like to know if there's a way that you can talk about what effect the Moon and the Earth have on Lagrange points for the Earth and the Sun. Like, how do those interact with each other?
They don't interact. It's just a solution of the three-body gravity problem. And what you will find is that there are these classical four Lagrange points, L1, 2, 3, and 4, two of which are stable, two of which are unstable. And that's just a part of a gravity solution for any three-body situation where you have body B orbiting body A, and A and B are both orbiting C in the case of Earth, Moon, and Sun.
Excellent. Thank you very much. The next question is from one of our live participants, Charlie Halls. Recent analysis of 100 million galaxies has revealed a new map of the distribution of dark matter. There is a suggestion that if it is accurate, it may prove Einstein's general theory of relativity wrong, though I don't fully understand why. Could you comment on this?
Right. The map that was released with great fanfare and publicity a week or so ago comes from what's called DESI, the acronym of Dark Energy Survey Instrument, operating in Chile, which has made the largest contiguous map of the galaxy distribution. This is, in the end, supposed to map out the galaxy distribution out to large redshift with large numbers of objects, and that allows us to map out the influence of dark energy on the cosmic expansion and the clustering of galaxies. Anything you may have read about general relativity being disproved by data from the dark energy surveys is actually not correct. There's nothing in the data that's been released so far that makes a threat to general relativity. In fact, this is interim data. They're only releasing a part of the survey. But they are defining the dark matter distribution at higher precision than ever before. And so that's going to be a constraint on the nature of the dark matter particle. That's what we might hope for from this survey.
And I think that leads right into Wiedemann's question, which is there any new data concerning the large scale structure of the universe? It sounds like this is something, and perhaps there are other pieces of information.
Yes, there are new surveys underway, and the Dark Energy Survey in the Southern Hemisphere is the best example. Basically, 4-meter telescopes, which are no longer cutting edge or state of the art, have been repurposed from being general survey tools with multiple instruments to being wide area survey tools with very sensitive and wide field cameras and CCDs. That is now the best use of 4-meter class telescopes because we now can make CCDs and tile a focal plane to get large area coverage, and a 4-meter telescope is big enough to go very deep. And so the Dark Energy Survey is the first example of this kind of use of 4-meter telescopes, which historically were used to observe individual objects more than half the time. Now they're being used almost exclusively or mostly for this kind of survey. And so these wide area surveys are going to start appearing more and more frequently. It's slow work, though. The Dark Energy Sky Survey is a 5-year project, and it's been slowed down a little by weather and the pandemic. So it's going to take 6 or 7 years to get the data out at the other end and properly interpret it. But these are now the best cosmological tools we have to understand on large scale structure the effects of dark matter and dark energy.
The next question is from Mashiriko. Is gravity a force? Einstein said gravity is a mere illusion. On the other hand, our school books say that gravity is a force. I'm in a dilemma about these two concepts.
Well, it's a good question because the recasting of gravity from Newton's theory to Einstein's theory really does take it away from the idea of being a force. In Newton's theory, you just have the idea of a force. You have two masses acting on each other with this force where the force is equal to the gravitational constant times the two masses divided by the square of the distance between them. That's Newton's classic gravity equation. And this force operates across a distance through the vacuum of space, apparently instantaneously. Einstein did replace this idea of a gravity force with the idea of curved space-time. So the existence of mass and/or energy distorts the space-time that those entities occupy, and it's those distortions of space-time, the curvature of space-time, that causes objects to move in orbits, light to be bent in gravitational lensing, and all the other effects we see in general relativity. And so it really is a sleight of hand to remove the idea of a force acting over a distance and replacing it with the curvature of space-time.
Excellent. The next question is from Murray, Switzerland, who asks, where in today's universe did the Big Bang take place? Can this point be considered the center point of the current expansion of the universe?
No, in the Big Bang idea, really, there is no center. There's no origin. everywhere participated in the Big Bang. So we see galaxies moving away from us, and running the clock backwards, all galaxies would be much closer together, the universe hotter, denser, and smaller. But if we were in a distant location in the universe, we'd see exactly the same thing. So every perspective is the same, democracy of perspective, and that means there is no center, no identifiable center, because the cosmic expansion included everything and is moving everything apart through expanding space-time. It's not necessary to invoke a center. There's no way to do it observationally. And so the concept and the question, unfortunately, doesn't have a proper answer. It's sort of a meaningless question in terms of Big Bang cosmology.
All right, the next question, part of it I don't understand. So Dark Seraph 88, if you have a clarification about the Shannon codes or binary codes, perhaps you could put that in there. I'm not familiar with those. But the question is, what are the exact differences between quantum leaps or quantum, I assume they mean tunneling, with electrons and pixels changing state?
Not sure where Shannon comes into that. That's a sort of different topic. Can you repeat the question? This is going to be a tricky one.
Yeah, so but the question that I will put forward is, what are the exact differences between quantum leaping with electrons and pixels changing states?
There's no obvious connection between these two things. Quantum leaping or electrons changing their energy state is about the quantized nature of energy and matter in the atom, and that's the fundamental insight of the quantum theory. Pixels are something completely different. Pixels are the sort of real estate of a screen or of a representation of an image in black and white, and they're not really subject exactly or directly by quantum effects at all.
Excellent, thank you very much. The next question is from Kelly T23. What do you personally really wish to investigate regarding the universe if you could use any instrument anywhere, everywhere with no limits?
Wow, that's a big question. I'd probably go in two directions with that. As a cosmologist, I would really like to know about the very first generation of galaxies, and in particular this chicken and egg question of whether the black holes that we see at the center of all galaxies now, that have often grown to very large mass, whether the black holes formed first from an early generation of stars, or whether the dwarf galaxies, the infant galaxies, formed first and then grew black holes inside them. That would be very interesting observation to make. James Webb Space Telescope will get us some way there, but probably won't answer that question. And the other one, of course, I'd like to know is there life in the solar system? And apart from subsurface Mars, which is the obvious place to look, I think the place that's of most interest is under the ice of Europa, the moon of Jupiter. If we could release a sensing robot under the ice, melt it through the ice pack, and explore under the ice for life, that would be a fascinating insight into whether there's life in the universe, life in the solar system beyond the Earth.
The next question is from Egil Skala. What are the differences between quasars and blazars?
So quasars and blazars are types of active galaxy. The general term for galaxies where there's something unusual going on in the nucleus is active galaxy. And as the term implies, these are not normal galaxies. Normal galaxies have a large density of stars in the center, but these active galaxies have something else going on. There's a very high density of stars, and it appears that there's a dark, massive object, supermassive black hole. And that supermassive black hole has an accretion disk around it. It's ingesting matter. It's accelerating particles and emitting intense radiation across the electromagnetic spectrum. So quasars are examples of that, supermassive black holes emitting a lot of energy. And the blazar category is a sort of subset of quasars, if you like, where it seems either that the jet is particularly strong or that we happen to be looking directly down the jet. And if you happen to have an orientation on an active galaxy where you're looking down this relativistic jet that emerges from the black hole region, then you have Doppler boosting of the radiation. So the radiation is enhanced by orders of magnitude, and the light is very variable on time scales of minutes even to hours and days, and that's what blazars do. They also have polarized radiation, which most quasars don't. So blazars are a particular subclass of quasars that give us a privileged look down onto the supermassive black hole.
The next question is from one of our live participants, Shanby Hogg. What is the next big event that's going to happen in this universe? It's a big question, and if you can answer that accurately, I think you'll win some kind of prize.
Well, the universe operates on cosmic timescales, of course. So the universe doesn't change dramatically from day to day or century to century or millennium to millennium. If we're talking about what we might see in the universe or what event might happen in the universe that's dramatic, that involves us or our future, I would say it's the merger and the collision of Andromeda and the Milky Way. So the Milky Way is moving towards the Andromeda galaxy, M31, at 100 kilometers per second. And if you do the math, that means in about 3 billion years, maybe 3.5 billion years, these galaxies will loop around each other. It's not a direct collision course. They'll be captured by their gravity, and the two galaxies will merge. Their supermassive black holes will merge. The interaction between the galaxies will eject many of the stars from either galaxy and send another set of stars into the nucleus to crash around and cause nuclear activity. That's a pretty dramatic event in the universe. Galaxy collisions and mergers don't happen very often, and in an average region of space, not very many at all. So that's the next dramatic thing that happens, where we'll have a ringside seat, or our distant descendants.
The next one is an interesting question, and you can take it in a couple of ways. Jalala Yemen asks, is there any change of the speed of sound at space?
Sound requires a medium to travel in. So sound is a compression and rarefaction wave. It's a wave not unlike light, which is a transverse electromagnetic wave. So because sound works by compression, rarefaction, in a medium, it requires a medium to operate. So there has to be a gas of some kind. Sound doesn't travel through the vacuum of space, and through the different atmospheres of, say, planets in the solar system, it would have different speeds. So the speed of sound does depend on the density and pressure of the medium it travels through. Speed of sound is only the value it would have on Earth in the Earth's particular atmosphere, and it will vary elsewhere in the universe. Now, sound can travel through a very diffuse or thin medium, and that's interesting because there are parts of space, say where stars are forming, where there is a very diffuse thin gas, and then the sound speed is actually very high.
Excellent. So this one has come up before, and I think at some point we will just need you to watch the video so you can understand where this comes from. But a couple of people are asking about a Veritasium video, so Veritasium, the YouTube channel, where he essentially claims that we can't technically know what the one-way speed of light is, and I believe we've brought this up before. But can you address the possibility that we don't actually know the speed of light, because technically, it could be different in one direction than the other, but we'd never know since we can't ever measure the one-way speed of light in one direction.
Right. So that's generally true. I mean, if we're going to measure the speed of light, say by bouncing a signal off of the moon, because we have a reflector on the moon, that's 250,000 miles away, then we actually have to wait for the round trip. However, in the laboratory, we could do experiments with light. And electronics is now so fast, essentially picosecond timing, that we can actually measure the speed of light and the way light moves through the lab, and we can measure it in different directions and orientations. So that's a lab scale experiment that does show that the speed of light doesn't seem to depend on orientation or direction or traveling one direction versus another. But it is true that we can't do that experiment beyond the Earth.
Excellent, and that's a really good point about being able to do that experiment on different scales. I'll have to watch the video again to see if he talks about that. And so I think that's really interesting. The next question is similar to an earlier one, but more specific. J-Lob would like to know, in your opinion, what are the 2 or 3 biggest questions facing astronomers or cosmologists that could be answered by the James Webb Space Telescope?
Well, the James Webb Space Telescope was designed to detect first light in the universe. That was its sort of killer app, if you like. So we hope it will answer that question. When was the first phase of star and galaxy formation after the Big Bang? We think it was within a couple of 100 million years of the Big Bang. James Webb, because it works in the infrared, can look at high redshifts, because this is highly redshifted radiation that we observe in the near infrared, although it was emitted in the optical and ultraviolet. So that's clearly a question James Webb was designed to answer and should be able to answer. Other questions that James Webb might answer are, it might be able to sniff the atmospheres of certain exoplanets to look for biomarkers. It's a very difficult experiment. James Webb was not designed with that in mind. That's another experiment. And the James Webb is also going to be able to do very deep galaxy surveys, which may give us a different type of handle on dark energy by measuring the way clustering worked early in the universe, or the way galaxies are moving at very high redshifts. And that's another way of getting a handle on the varying relative amounts of dark energy and dark matter.
The next question is from Jan Campos, who sent an email. How would physics change if we had a complete theory of everything? Would we know what dark matter and energy are? Would it help us better understand consciousness?
That's a good question. And the theory of everything that people allude to is a theory that unifies essentially the four forces of nature. So it's a sort of super theory from which the four distinct forces that we observe in our universe derive. Some people think it will be a string theory. Other people are not so sure. We simply don't know. Having this theory will not actually make our predictions of low energy phenomena like in the present universe any better. It'll just give us a much deeper view of how the laws of nature are put together. And that's important in its own right. But as far as practical matters go, it won't actually have a dramatic difference on terrestrial or lab scale physics. However, we hope that the theory of everything will have observational consequences. Perhaps if it's a multidimensional theory, we'll get to hints of what these extra dimensions are, or what their scales and energies are. And that would lead to a new set of phenomena that we could explore.
The next question is from Alexander B. Is there a noticeable difference in gravity on any point on the Earth, or is it unified or the same everywhere?
Actually, we can map the gravity of the Earth in detail. So gravitational experiments are pretty sensitive. And in fact, we've used gravitometers, or gravity meters, to map out the varying density of the Earth. So the Earth, of course, is not uniform in density. It has variation, not just internally and radially, but it's not a perfect sphere either. And so we can actually map out the variations in the surface gravity of the Earth, around the Earth. And these are very subtle variations for tiny fractions of a percent, but the instruments are good enough to do it. And that, of course, gives us a very interesting insight onto the internal structure of the Earth.
The next question is from Tapas Mehta. What exactly is time, and how is it related to the Big Bang?
Time. So time is a quantity in physics that relates to how we track events. So things happen in the natural world, and we can tag the things that happen with a time and a place. So we can imagine X, Y, and Z, and T for the time axis. And that's what space-time is in general relativity. So in general relativity, time has a particular attribute where it is coupled to space. And depending on the situation, the gravity situation, this relationship between time and space can be quite profound. For example, when space is highly curved, we actually have time dilation and time slowing down. So in the modern theory of gravity, general relativity, time has an interesting property. It just does not flow uniformly and independent of space, but it's actually tightly coupled to the way space behaves.
So we have a slight clarification to an earlier question about the Shannon codes. It sounded like you had at least heard of those. I guess James Gates Jr. claims to have found these Shannon code or binary codes using supersymmetry and the same equations that are used to describe the elementary foundations of the universe. Are you familiar with that? Can you talk about those, or is this further out?
I have to punt on this one. I haven't heard of this. I mean, I could investigate.
Fair enough.
It's not familiar.
Okay, sounds good. So the next one is from Rishabh Chowdhury. Can you please give us any insights on black holes and black hole evaporation seems to violate the rules of quantum mechanics. How close are we to really being able to understand black holes?
We are some way from understanding black holes. Black hole evaporation does not violate quantum mechanics per se. Evaporation is actually a prediction of the quantum theory. So when you try and include gravity and the quantum theory together, remember we do not have a unified theory of those two forces. We don't have a quantum scale theory that merges with a gravity theory. But when you try and reconcile them or try and work with them in the same situation of a black hole, then it is the quantum theory that lets you predict that black holes have a temperature and that they should evaporate. So the evaporation is actually a prediction of the theory. It's not a violation of the theory. However, our theory of black holes is, of course, incomplete because we haven't resolved the issue of the singularity. We haven't resolved the issue of what happens at the event horizon. Is there a firewall? How do we resolve the information paradox? So there are many mysteries of black holes, and they essentially revolve around the fact that when we use quantum theory to apply to a black hole, we're kind of grafting on quantum theory to a situation that it wasn't designed to explain.
The next question is from Shriyanak, who asks, what are your thoughts on a fourth or more spatial dimension? Is there any way to detect these additional spatial dimensions? We just can't perceive it? Or do you think we really just live in 3 spatial dimensions?
To all intents and purposes in terrestrial physics and lab experiments to this point, we live in the 3 dimensions of space and 1 of time, and that's what general relativity describes quite beautifully. String theories, frontier theories that try and unify the 4 forces of nature and reconcile gravity and quantum theory, often involve multiple dimensions, 10 or 11 dimensional space-time. And in those theories, there are extra hidden dimensions. They're hidden because they operate on incredibly small scales and high energies, and they could only be accessed in that way. So the question becomes, are there any manifestations of these hidden dimensions for lab scale physics and energy scales that we can work with accelerators and laboratory equipment? And nobody knows. The answer is we don't know. So there have been no signatures of hidden dimensions yet in any lab experiment I'm familiar with, but there are some clever approaches to this that potentially could hold some success. So at the moment, extra dimensions is a pure hypothetical construct out of string theory with no experimental support.
The next question is from Remus Romania, who asks, could we build a balloon? And they give some specifics like with heated hydrogen. But the basic question is, could we build a balloon to explore the high latitudes of Jupiter, where the wind speed is very low compared to the equator, and study the atmosphere at the base of the clouds?
We could explore the cloud decks of Jupiter with suitable equipment. The base of the cloud decks is a very bizarre situation. Jupiter may not actually have a completely solid surface. As you go down in the atmosphere and the pressure and the density increases, the dominant ingredient of hydrogen actually starts to take a metallic state. So it's almost like liquid metallic hydrogen. If there is a rocky core to Jupiter, this metallic hydrogen sort of merges with the rocky layer and almost that there's no solid surface. Now that physical condition of pressure and temperature is such that no spacecraft we know of could survive. So the best we could do with Jupiter is explore the upper cloud decks, which have a sort of temperate temperature, sort of like the Earth's temperature, because Jupiter is far from the sun. So outside is very cold, and then the interior by pressure is superheated.
The next question is from Rentgen 101. Can you talk about the early oxygen levels on Earth before photosynthesis?
Right. The very early Earth had no oxygen. So the early Earth was a hydrogen-rich or reducing atmosphere. There was also a lot of methane and a lot of carbon dioxide, more than we would see now. The first oxygen was produced, the first microbes were methanogen oxygen. They had a metabolism that was based on methane. And the first microbes that produced any oxygen happened about 3 billion years ago. And that was the beginning of the genesis of oxygenic photosynthesis that built the atmosphere up to its current oxygen level. But the oxygen level took a long time to reach its present level. 3 billion years ago, oxygen level was maybe 1 or 2% of the total atmosphere. I didn't get up to the current levels of around 20% until a few 100 million years ago. It went in stages. Actually, when oxygen was first produced, it became toxic to some of the microbes that already existed. And so new forms of metabolism had to be invented. The history of oxygen is a very interesting part of the Earth's history, and we don't fully understand the details.
The next question is from Shrianek, who asks, is it possible that a star could turn into a planet? And if so, how?
No, planets and stars are really distinct almost by definition. A star is a self-gravitating sphere of gas where the temperature in the interior is hot enough for fusion to occur. And that means it's a plasma, so it is not solid at all. Whereas a planet is a rocky and icy body that may have a gaseous envelope, but it's basically a rock. And so stars and planets, almost by definition, are really distinct objects.
The next question is from Dark Seraph 88. What would happen if an astronaut brought a glider up onto the International Space Station and jumped off of the space station? Could they move around with any control, or would they just not be able to do anything until they run out of oxygen?
A glider? Was that the first part of the question?
Yes, I'm sorry. It was some kind of a glider with wings,
so
would they be able to move around?
A glider from the space station would not function at all, because the space station is at 300 miles altitude where there's essentially no atmosphere. And so a glider would have no aerodynamic properties. So if you left the space station and you perturbed yourself so you were out of an orbit, then you would just start a slow accelerating free fall to the Earth. Now that the highest skydiving that's happened has been from elevations, I think, of about 100,000 feet up, which is nowhere near a space station level, but it's above essentially all of the atmosphere. And that's an incredibly scary free fall going to hundreds of miles an hour. So a glider would not operate, and gliders really can't operate much above 35 or 40,000 feet because the air is too thin.
The next question is, will we be able to see details of exoplanets with the help of the James Webb Space Telescope, or do you really need something larger to be able to see those kinds of details?
Yeah, that's a good question. We do want to see exoplanets in more detail. We've measured and detected thousands of them, but they're essentially pale blue dots. They're just dots, single pixels, if we can make an image at all. So of the 4,000 or 5,000 exoplanets known, only 100 or 150 have been imaged, and they're just single pixels. So there is no ability to map an exoplanet yet. And indeed, it would take a next generation of telescopes, 10, 20-meter telescopes, perhaps in space, to be able to actually see the exoplanet in detail. And even then, it won't be in detail. Just to get to the point of resolving maybe 10 by 10 pixels or 100 total pixels, and therefore see large cloud decks or continents and oceans, is beyond current capabilities and probably 20 years away.
So this is kind of an interesting question as well. Is it possible that we could use the sun as a gravitational lens, for a telescope, say, to map distant objects or distant exoplanets?
Yes, has been a thought and a proposal. It's not funded in any way, but there is a thought of being able to use the sun as a gravitational lens. You have to do the math of the bending of light by general relativity and figure out what the focal point of distant rays grazing past the sun is. And if you assembled a telescope at that location, which is of course nowhere near the Earth, it's actually very far away, then you in principle could use the sun as a gravitational lens. And if you move that telescope around, then the sun would be focusing light from different regions of the sky. So there's a concept out there of using the sun as a gravitational lens. It's an extremely powerful thing to do if you could do it. because that lensing, that magnification and amplification actually does let you see incredibly faint objects, and in principle with very high resolution as you move across the focal plane. So it's a fascinating idea. It's a pure concept at this point. There's simply no way for us to do the engineering, and I don't even think I've seen a proper cost analysis.
Excellent. Thank you very much. The next question is from one of our live participants who asks, do the laws of physics allow the realization of a warp engine as described by Miguel Alcubierre?
Yes, this Cuvier warp drive, which came into the news a decade or so ago, it on its face violates the laws of physics because we have no observation of tachyons or faster than light particles, and there's no clear mechanism to generate faster than light travel. Although you can transmit with a phase velocity faster than light speed, you can't transmit an object or true information beyond light speed. So it's a controversial idea, and it hasn't, of course, been demonstrated in practical terms. So I think the jury is out, and people are basically skeptical because on its face it violates special relativity, which is a very well-tested part of Einstein's theories.
The next question is from Mesh Rico, who asks very dramatically, will physics collapse if an object faster than light is accidentally discovered? But really, what would happen? What would we do? What would physics do or change if something faster than light is discovered?
Absolutely. I mean, the good thing about science is we can't have opinions or dogma to fix because we've found out a lot about the universe by discovery and experiment. So I think science is empirically based, and a result of observation. We form theories and we test those theories and improve them and sometimes throw them away. If faster than light objects were discovered, tachyons as they're called, then physics would have to accommodate them. And that would be an extension and perhaps a rewriting of current physics. And that's simply the way science works. So it would be a very exciting eventuality. I think most physicists would view it very favorably, in fact, because we're always looking for new phenomena to test our theories with.
So I will let you give your view on this. Let's see, Delali UXA asks, is it possible to capture live footage of blue jets and elves in the ionosphere? And I will say that if you look for blue jets and upper atmospheric phenomena, you actually can find pictures now of those, but they were elusive for a long time. So Chris, can you talk a little bit about blue jets in the upper atmosphere? Or these
actually, I can't. I don't know about those. I have to look that one up.
Sounds good. So, but if you look at upper atmospheric phenomena, there are now pictures of some of those things on even just on Wikipedia. So take a look. So Arnav Asby asks, what is the importance of dark matter, and what information about dark matter is still unknown to us?
The importance of dark matter is that it is 5 or 6 times as abundant as normal matter. That is, the baryons we're made of, protons, neutrons, and electrons. And it binds galaxies and forms most of the large-scale structure in the universe. So galaxies would not be intact as discrete objects without the dark matter halos they're embedded in. So its importance is in accounting for all the large-scale structure in the universe we see. That's its importance, and understanding its nature is one of the biggest questions in cosmology. We have astronomical observations of dark matter and its distribution and its behavior and rough properties, but they don't tell us what it is. It's likely that if it's a fundamental particle, the actual determination of dark matter's nature will come from laboratory experiments or deep mind experiments, and we hope that happens probably in the next 5 years.
The next question is from Jalal Yemen, who asked about time, but we've talked about time quite a bit. So the second part of the question, though, is how do space probes make it past the asteroid belt without crashing into asteroids?
That's a good question. First of all, remember that the artistic representation of the asteroid belt is almost completely wrong, almost always wrong. Even NASA has some visualizations that are not very accurate. Even though the asteroid belt has a lot of objects, millions of rocks in a thin belt, that belt is actually distributed over millions of miles radially, and the actual density of those rocks in space is quite low. And so it is actually possible to traverse the asteroid belt with a modest and small probability of having an impact. If you do have an impact, of course, it's catastrophic. So it's a loss of your telescope or your space probe. So NASA and other space agencies will, of course, avoid the asteroid belt unless they're sending a mission to inspect it in detail. But actually, the odds of a collision are still fairly low.
The next question is from one of our live participants, Prachidi. So we've recently learned, or sort of in modern times, we learned about the collision of molecular clouds forming new galaxies. But how long ago did these collisions happen? And is it possible to see direct effects instantly from these kinds of collisions?
The collapse of clouds, including molecular clouds, to form star-forming regions and galaxies, we can observe places where this is happening now. I mean, it's not now, of course, these are distant objects, so there may be look-back times of tens or hundreds of millions of years. But we can watch this process happening at different stages of its evolution. And so we think we can see the stages of how galaxies form. And indeed, the clouds collapsing, forming a burst of star formation, is an early part of most galaxies' evolution. The star formation rate overall in the universe has declined dramatically by 2 orders of magnitude from about 7 or 8 billion years ago. And in an individual galaxy, the star formation is intense early on as this compression and collapse and collisions are happening, and then gradually it tails off, as happened in the Milky Way too.
The next question is from Mashriko. You talked about microbes having a metabolism related to methane. Is it possible that living organisms could evolve and respire using other reactive gases like chlorine or something other than oxygen?
Yes, there's speculation amongst astrobiologists that you can have metabolisms with various different bases. On terrestrial microbes, for example, we found methanogens, we found microbes that metabolize methane, also hydrogen sulfide, and there are even microbes that are able to metabolize heavy metals, which are toxic to humans. So you can have free energy in a chemical sense from various compounds, including things that are toxic to us, and a variety of these have already been found in terrestrial microbes.
The next question is from Astronomy Interested. How do spacecraft move in space while there is no air and therefore no pressure could be made to move the spacecraft forward in space?
So the principles of rocketry are based on Newton's laws. Basically, Newton's third law: for every action there's an equal and opposite reaction. So the basis of a rocket is to combust a gas. We're talking about chemical or liquid fuel rockets. Is to combust a gas, and in that combustion, heat it up and eject out of a nozzle at a very high velocity. And so that small amount of mass going at a very high velocity has a certain momentum, and that generates the much larger mass of the spacecraft going in an equal and opposite direction at a more modest velocity. So basically, we're trading off a action and reaction, where the exhaust from a rocket is what propels the rocket forward. So there's no medium required for this. It's just an application of Newton's third law.
And then as a follow-up, how do spacecraft change directions in space? So obviously they could use rockets if they needed to move directions, but are there other mechanisms?
No, usually spacecraft have main rockets for propulsion, and then typically they'll have smaller rockets around their periphery that are retros or side-facing, and those will basically steer the rocket. Sometimes a spacecraft will have its main rocket engine mounted on a gimbal, which allows the orientation of the main rocket to change, and that's another way of changing the direction of the spacecraft.
Excellent. Dark Seraph 88 would like to know if you have a favorite scientist or physicist or astronomer of all time. So who are some of your heroes that you look up to?
Well, of all time and historically, I mean, Newton is hard to beat. He was the titan of physics, the sort of head and shoulders above everyone else, inventing this incredible theory of gravity that lasted for 300 or 400 years until Einstein came along. Einstein, of course, is another classic hero for most physicists. Of living physicists, that's an interesting question, or astronomers. There are a number that I look up to, a number that I admire. There are some very impressive people who've made amazing discoveries. I think one I might pick out is Kip Thorne, who was a gravitational theorist at Caltech, winner of the Nobel Prize for the LIGO experiment. Really a brilliant theorist, deep understanding of massive black holes, of gravitational waves, also a great expositor of science. He's written popular books as well. So of living scientists, I might pick out Kip Thorne, who I met and knew moderately well when I was a postdoc at Caltech.
That's very cool. David Learning would like to know, what is the best example where length contraction from the special theory of relativity is taken into account in astronomy?
That's an interesting question, and typically that doesn't happen because the Lorentz contraction, as it's called, the sort of part of the apparatus of special relativity, it would require a macroscopic object, that is a real physical object, to be accelerated at close to light speed. And of course, the energy requirement to do that is prohibitive. So actually, Lorentz contraction is not really routinely observed. Particles can travel at close to the speed of light, but particles like electrons or protons are so small we can't measure their size, and we couldn't measure their Lorentz contraction. So of all the effects of general relativity, Lorentz contraction is one that's actually not been observed astronomically.
The next question is from C. Blakemore 01. Rather than dark matter, could the missing mass be a superabundance of micro black holes?
So one of the candidates for dark matter is of course microscopic black holes. The only niche available is for the very small black holes. We can rule out normal sized dead star black holes because that amount of black holes to make, for example, the halo of our galaxy would cause microlensing or deflection of light in experiments that we would have seen it decades ago. So we can rule out those kind of black holes. The niche that's available are called primordial black holes. So in principle, out of the early dense universe, space-time was compressed and in such a churning state that you could have microscopic black holes. By theory of Hawking radiation, those black holes would evaporate, but there is a small window of black holes where their evaporation time is as long as the age of the universe so far. And so those black holes, which are very small, maybe a fraction of a gram, 10 to the minus 5, 10 to the minus 6 grams, would survive until the present day. And that's the window of black holes that people are still looking for to potentially be the dark matter. But it's actually difficult with that theory and that window to make enough microscopic black holes to account for the dark matter we see.
Martin Gillum sent an email asking, you've spoken of black holes having a jet. So does this propel the black hole forward, or are there other factors that would keep it relatively anchored in one position? Like do these jets move black holes around the universe? Are they mobile?
That's a good question. The jets that black holes make, because they're spinning objects with angular momentum, are bidirectional jets. So in most manifestations of a spinning black hole at the center of a galaxy or an isolated black hole, the jets emerge along each pole where the density is low, and so that's where the relativistic plasma can escape. So there's no movement, or there's no recoil, if you like, of the black hole from the jets. They don't actually carry that much momentum either. So black holes appear to be bidirectional. We don't always see the two directions of the jet because the jet that's more pointed in our direction is amplified by relativistic boosting, whereas the one pointed away from us is not. So typically it's the near jet, or the jet pointing in our direction, that is brighter and we see it, whereas we don't always see the counter jet.
Excellent, thank you. So the next question is one that we haven't discussed in a while. How often does the sun's magnetic field flip?
It's every 22 years. That's the solar cycle. And we can map that with the sunspots, which the rise and fall of the sunspots twice during a total solar cycle, a full double reversal of the magnetic field, is our tracer on the surface for the magnetic field. These sunspot pairs are where magnetic field lines erupt through the photosphere, and that's what lets us see the magnetic field, which otherwise would be invisible. So this is the solar cycle, and we've mapped it, of course, directly since the invention of the telescope, so for about 400 years. But there are more indirect ways of mapping the sun's magnetic field activity and its sunspot activity through the geological and climate record of the Earth. But these are much less direct than counting sunspots.
Excellent. So it is 10:52. I want to make sure and give you plenty of time to get to your next appointment. So I think this will be our final question for today. But I think it is an interesting one. It gets us into astrobiology. I know that it's not a dominant theory, Delalia UXA asks, but what are your thoughts on the possibility that life on Earth originated from Mars? And how would that change our thinking if the rovers on Mars discovered such a thing?
Yeah, first of all, the rovers unfortunately do not have pure, actual life detection capability. But if at some point we did find life on Mars, under the surface perhaps, it is indeed possible in the panspermia idea that life travels around the solar system. And because Mars has a thinner atmosphere and the gravity is weaker and the Earth is closer to the sun, those are three reasons why a rock is far more likely to travel from Mars to the Earth than the other way around. So technically, and by that calculation, it is entirely possible that many Mars rocks have landed on the Earth, and they could have been life-bearing. And it could have happened, say, 3 or 4 billion years ago when Mars was warmer, wetter, and almost certainly fully habitable. So it's going to be hard to rule out the fact that life on Earth originated from Mars, given that situation. The only way we could rule it out is with the counterexample. If we found life on Mars and its genetic basis was different from that on Earth, then we know that was an independent origination. Okay, thanks. That was a good question to finish with, and appreciate the variety as always. And we'll be back with you in a couple of weeks. Thank you. Thanks to Matthew for facilitating, and Vicky too, behind the scenes.
Excellent. Thank you all for joining us, everybody. And we'll see you in 2 weeks. And that next one will be in the afternoon. We'll send out an announcement. Take care.